Or oh, can you all hear me? Is it fine? Or maybe
What's it? I mean, I can hear you pretty
Oh,
much
sorry.
better. Yeah, it's
Wonderful. Okay. Thank you. Yep. All right. Hello, everyone. My name is Stefano Bellotti, and I'm a postdoc researcher at Leiden Observatory. First of all, thank you very much to the organizers for giving me the opportunity to present my work, which is going to be about searching for magnetic cycles for solar-like stars for a specific sample observed within the BCool program. Now, a little bit of motivation behind this, or maybe not. Let's say. Yes, exactly. Thank you. So, well, motivation is that although the sun has been observed a lot and we've come a long way in terms of dynamo theories, in terms of understanding the generation and sustain of the magnetic field throughout the lifetime of the star, the sun is one data point. And don't get me wrong, I appreciate the sun, especially since I moved to the Netherlands, but we need to go out there and look at more stars, especially solar-like stars. And because with that, we can provide observational feedback as well as context and tests for the dynamo theory. But it's also important for exoplanets because the magnetic field regulates the environment in which planets are embedded and that are showered by these magnetic phenomena. So it is important also to characterize the magnetic fields of these. Now, of course, the sun is an important benchmark here, and because we're talking about cycles, I cannot not proceed without showing the magnetic butterfly diagram. We have like a series of magnetograms here. In particular, I have the latitude on the y-axis over time, and the intensity of the longitudinally average magnetic field intensity is given by the color bar. So we see that we have the formation of magnetic spots at plus or minus 30 degrees in latitude, that they converge towards the equator as time goes by. And in particular, this occurs over a timescale of 11 years. We have an activity maximum around, we have a polarity reversal around activity maximum every 11 years. And to restore the same configuration as of the magnetic field, we need 22 years, more or less, which is the timescale for the magnetic cycle, or also known as Hale cycle. On the large scale, the magnetic field is predominantly poloidal and dipolar. Now, around activity maximum, the higher order modes increase, so it becomes more complex, as also Marco was showing in the previous slide. But and also the axisymmetry, meaning the obliquity between the magnetic field axis and the rotation axis changes over time. So we have this information on the large-scale field, which is going to be our benchmark and important for later. Now, when we go out there and look for other stars, and in particular, if we want to characterize the topology of other stars, we use spectropolarimetry. This is a specific technique that exploits the Zeeman effect, basically what happens to atoms and molecules when they are immersed in an external magnetic field. What happens is that the energy levels split, and we have more lines, more absorption lines, for instance, and we have and they have different polarization properties. So by studying these polarization properties, either in circular or linear polarization, depending on the star, we can infer properties on the magnetic field of the star. We need high resolution in particular, and we also need either circular or linear polarization. Now, because the stars are point-like sources, we have to deal with disk integration, and therefore we will not have spatial resolution. So we will not be concentrating on the small-scale fields, but only on the large-scale magnetic field. And in particular, the technique that I'm going to talk about, that I use primarily, is Zeeman Doppler imaging. This is a tomographic inversion technique that allows us to invert a time series of circular polarization profiles into a magnetic map of the stellar topology. We need the Zeeman component, which means we need the field to be detectable, and we need the Doppler component, which means that we need to sample the rotation of the star. We have to look at the star to monitor the star in order to sample the various longitudes. This is what is shown on the right with this GIF, where it's basically the forward problem. What would a patch of a magnetic radial field coming outward look like as the star rotates? What we want to do is to see this evolution in the magnetic field, in the polarization properties, in order to infer the magnetic field. Again, this is an academic case in this GIF. This is an illustrative purposes. We will not have this kind of spatial resolution. But not only I'm going to talk about Zeeman Doppler imaging, but also Gaussian processes very quickly, because what we can compute when we have circular polarization observations is the longitudinal magnetic field. This is the disk-integrated line-of-sight projected component of the magnetic field, which is modulated at the stellar rotation because it's sensitive to the various patches, to magnetic field patches on it. And what we can apply is Gaussian processes, which are powerful statistical tools in order to basically fit functions and infer the evolution over time of this quantity. And in particular, I'm showing here that I used a quasi-periodic covariance kernel for the model. Now, let's get more into the projects. So we have data from the BCool program. This has been going on for a while. We have a baseline of 12 to 15 years, depending on the star. And the the observations were collected in the optical domain with Esperance at Canova-Francois telescope, or Narval or its upgrade to Neo-Narval at telescope Bernard-Liot in France. And I have 6 stars shown here within their parameter space. They have up to 6% the mass of the sun and up to 200 Kelvin hotter than the sun. The rotation period instead spans a wider range. We go from 3.5 days to 22 days rotation period, which means that this is a suitable sample to pretty much study the nature and the existence of the magnetic cycles based primarily on the rotation period. Because, in the interest of time, I'm going to divide this sample into slow, mid, and fast rotators, and I'm going to talk about 1 star for each of these categories. Let's start by HD 9986. This is a slow rotator in the sense that it has a rotation period of around 22 days. And as we can see here, the longitudinal field in green, we have the data points, the x-axis is time, of course, and the purple color is the GP model, the Gaussian process model. We see that the bulk of the measurements at the beginning were pretty much positive. They began negative and then positive again. And the GP captures this evolution of about 11 years. And then we apply Zeeman Doppler imaging. We have, for instance, these magnetograms, which, as Dag Eversberg was showing before, in Cartesian coordinates. In this case, these are it's a polar projection, which means that the pole is at the center and concentric circles indicate decrease in latitudes. This equator is shown as a solid line. And we have also 3 different components, the radial, azimuthal, and meridional field, because it's expressed in spherical coordinates. Now, when we perform this for all the epochs that we have, this is what we see. The negative is the blue is the negative polarity and the red is the positive polarity. As we can see, we obtain 2 polarity reversals because we started with a pretty much positive magnetic field, which became negative in the subsequent 3 epochs, and then positive again after 5 years between 2012 and 2017. These are basically data points that encapsulate the topology here. I don't have time to explain that. These are confusogram data points. Eventually, we can talk about it later, but basically they summarize what we're seeing here. And therefore, we can pretty much see that there is an analogy with the Hale cycle of the sun, but the timescale is faster. We have a magnetic polarity flip of about 5 to 6 years, which means that the magnetic cycle timescale is of between 10 and 12 years, so twice as fast as the sun. Then we have another example, but in this case of a mid-rotator, HD 76151, with a rotation period of 17 days, more or less. And here the situation is a bit more complex, because as a matter of fact, we see that there are faster variations. In particular, this is a good case to show and appreciate how yearly cadence allows us to see fast variations of the magnetic field that we may have missed in the first part of the time series. Now, when we make the ZDM maps, we see that the situation is a bit more complicated to explain because we see that the magnetic field is pretty much poloidal, dipolar. The axisymmetry varies over time, but we mostly see only one dominant polarity for most of the epochs. Perhaps in 2019, in 2019, we have a little bit more positive polarity. So it means that we may have just missed the polarity reversal. So in order to explain this, there are two possible scenarios. One is a fast cycle of 2.5 years, and we were very unlucky because we only captured the negative polarity. Or what happens is that we have two cycles superimposed to each other. We have a fast cycle that determines the fast oscillations in axisymmetry, and a longer one with a known timescale that the polarity reversals would be synchronized to that. And therefore, we need further monitoring of the star to better constrain that for this case in particular. And this is not unheard of because there are other stars like Epsilon Eridani and V889 Hercules that also show superimposition data points could be explained by superimposition of cycles. Finally, we have a fast rotator with 3.5 days rotation period. In this case, the situation is, again, a bit complex. The values are pretty much positive, but there is a lot of scatter in the longitudinal field. This means that the field is either very non-axisymmetric or complex. And as a matter of fact, when we look at Zeeman Doppler imaging maps, we see that the radial field in particular is quite complex, and it doesn't show clear signs of a cycle. We have an intermittency in the strength of the magnetic field, but pretty much the topology remains complex overall. So in this case, we cannot really talk about magnetic cycle timescales, but more magnetic evolution timescales, because the field is evolving. For instance, we see that the polar regions here are mostly positive, and then they become negative over a month, but it doesn't really show signs of cycles. Now, this is my last slide with the conclusions and the summary. Basically, by monitoring the long-term evolution of magnetic fields of solar-like stars, we've seen that there are stars, slow rotators and mid-rotators that show Hale-like cycles with a faster timescale. There is a particular case that is doing something weird, and it's better to pretty much monitor it more to understand better what it's doing. Perhaps the superposition of two cycles. And finally, we have the fast rotators, which are not really showing signs of cycles. So there is a dependency overall of the existence of the magnetic fields here, of the magnetic cycles here based on the rotation period. And with that, thank you very much, and I'll take questions.
In Colorado. As I recall, the Mount Wilson LC2 observations over a long period of time showed exactly the same results, namely that the slow rotators showed cycles, magnetic cycles, although they weren't measuring magnetic fields directly. And the fast rotators were just complex and no obvious cycles. Would you comment on that?
Yes. Basically, we are seeing, so thank you for that question, because I have a few extra slides. We computed chromospheric activity indicators here as well. I'm showing here the longitudinal magnetic field at the top and the S index at the bottom as well, in the middle panel, and the magnetic topology in the bottom panel for the different stars. So we also kind of see a variation in the chromospheric activity indexes here, but it's not necessarily correlated with either the longitudinal magnetic field value or the topology. So it really depends, as opposed to, for instance, the sun that has the chromospheric cycle is synchronized to the topology cycle as well. Thank you.
Okay, our next speaker is Laura Dreesen from Sydney University.
Okay, hello everyone. Yes, I am a stellar radio astronomer, which I understand confuses both radio astronomers